Welcome, everybody. English, what are you doing already? How are you mentioning my video 7 seconds in? Oh my God, just take my paper away from me. I can't teach anymore.
Special guest.
No, he's not that special. Alright, so, interrelated rates. Everything we do, we've been taking derivatives with respect to x. That's going to change for this one, because we're going to do word problems. And every single word problem we do is going to involve time. So we're going to start taking the derivative with respect to time. Okay? So, this first one right here. I'm going to take the derivative of each side of the equation with respect to time. What's the derivative of p with respect to time? Anybody? This is not 0. It's not a number. It's going to be dp dt. That is the derivative of p with respect to time. Equals, what's the derivative for x with respect to time? 4 dx dt. How are we doing? We are tagging absolutely everything with respect to time. Everything. Well, no, 4 is just 4 is part of that function. So on number 2. By the way, this is area represents what? Area of a square is fine. Rectangle. Could be a parallelogram, quadrilateral where we have the height and the base. Not a trapezoid. So, what's the derivative of a with respect to time? dA over dt equals I have b times h. I heard somebody say it in the distance. What is it? It's product rule, because we have a product of 2 functions. Woo! Me love some product rule. Here we go. What's the derivative of the first? So what's the derivative of b? dB over dt times h plus b times. It's beautiful. All right. Try 3 on your own. If you think you're good on 3, try 4, and then we'll come back together in about 30 seconds here. All right. Take a pause for the cause up here for number 3. We're going to get dA over dt equals. I'm just going to keep that 1/2 out in front. And then I have a product rule. So it's going to be dB dt h plus b dH dt. And then if you want to distribute that half ahead of time, I don't really care. It's not a big deal. So some people will have like 1/2 dB dt h plus 1/2 b dH dt. It doesn't really matter. So we have a rectangle, we have a triangle. This number 4 is going to represent a circle. What's the C represent of the circle? Circumference. So what's the derivative of this then? dc dt equals 2 pi dr dt. So far, everything's been pretty simple. Every single function I've been taking the derivative of has been linear. Nothing weird. And that's going to change. What's 5 represent? Area of a circle. So let's go take the derivative of the left side. What do you get? dA over dt equals, what's the derivative of r squared? So it's going to be 2r. So it's going to be 2 pi r with respect to t. So it's going to be dr dt. This is a whole lot of chain rule. No, because what's the derivative of r? Just 1. So it's really 1 times dr dt. So there's like a hidden chain rule inside of there. Try 6 on your own. If you think you're good, go ahead and try 7. I'm not going to go through all of these because it's just, I don't want to waste your time. Time.
Oh, ha. That was pretty good. I'm in third mode, not last mode.
You have to learn to be in each mode at all times. So trying out 6 and 7, and we'll talk about what shapes they are. All right, number 6. First off, what does number 6 represent? What's V represent in the math world? Volume of what? In this case, it's going to be all sides are the same. The cube. So this is going to be dv dt equals 3x squared. What does 7 represent? That Pythagorean theorem thing. So what's the derivative of x squared? What about y squared? Someone just said z, and I wrote a z. Equals, and then I heard someone say it. So 2z dz dt. All right, so we get the idea of this. I'm not going to do all of these because we don't need to. No. But so I'll leave some of this. I'm going to skip down and do a couple more. I'm going to leave some of this for you to do on your own if you're struggling with taking the derivative, because for the related rates, there's 2 steps. There's 3 steps. First step, setup. That's the hard one. Second step, derivative. That's this right here. Third step, plug everything in and solve. So setting up is usually the tougher one. I'm going to skip down here to number 11 real quick. Does anybody know what number 11 represents? Volume of a sphere. Very good, because it's got 3 radii. So there it goes radii in each direction in terms of horizontal, vertical, and our third dimension. So this is going to be dv dt equals 4/3 pi times, what's the derivative of r cubed? dr dt. Okay, and then the other one that's important for today Again, there'll be a key of this on Canvas. It's going to be number 15. I'm gonna make a slight change to it. I'm going to do like cosine of theta equals, I'll do a over 2, just to keep it a little bit on the simpler side, because I don't think we're ever going to do we're not going to have 3 variables like that. So what's the derivative of the left-hand side? It's negative sine. Negative sine theta. Tag it. D theta dt. Equals, and what's the derivative of a? So this would be d over dt. So can we just say this is 1/2 dA dt? So there's this trig stuff that appears a little bit as well. It's not as common in related rates, but it will happen every once in a while. Towards the end of this unit, this short unit, I do have a circuit that has some of the toughest related rate problems you'll see, some of the toughest optimization problems, because I figured if you can do the tough ones, you can do the easy ones. Not a big deal. All right, let's go ahead and get to so this you can finish on your own time. Now that we're kind of warmed up, let's get into related rates. So I'm not going to do all this because we kind of just did this. I did this a little more in a relevant fashion for when we're actually going to be doing it. This is the top part, kind of sort of relevant, but I've done it already. So related rates are questions that ask for a calculation of a rate at when it changes. So we have a variable change on a rate of another variable known to change. This is all related rates. Okay, it's probably easiest just to start doing problems. Okay. When we start doing problems, I'm going to kind of move down here to the steps. I don't actually do these exact steps in this order, but what I do... Okay. That wasn't a joke. That's just me not understanding English and making sure I'm good. You need to state givens. You need to state givens. This is kind of like what this says right here, but this is just how I do it. So I'm going to state givens. What are we finding? And what formula do we use? So we're going to state the givens. What are we finding? What formula do we use? About it. Let's just flip the page and start doing problems. Let's do it. Okay, number 1, we're going to have a pebble. We're going to drop it into, it says a calm pond. That just means everything's smooth, like there's no waves or anything, so nothing's going on, and then we drop a pebble into it. It causes ripples in the form of, I can't read, concentric circles? What does that mean? Existing circles. Circles within circles within circles. And I don't. That just tells you how important that is. Just understand what happens, what it looks like when you drop a pebble into water. Okay, the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4, what is the rate of the area of the disturbed water changing? So let's go through and let's do our givens. So, whenever we have this something per something, that's going to be a rate. Okay? So this first thing we're given is a rate. It says the radius is increasing at that rate. So that's going to represent dr over dt. That means the radius is doing something over time. And what is it doing over time? It's increasing by 1 foot per second. What else do I know? Radius is 4 feet. Anything else that I know? Okay, so what are we looking for? Looking for area or the rate of area? Those are two different things. What is the rate? What is the rate? We're looking for the rate. I'm not looking for A. I'm looking for dA over dt equals question mark. Okay. Sometimes we need helper equations for these. Sometimes they're very straightforward. This is a very straightforward one. So we need to think of a formula that somehow relates an area with a radius. What formula do we know that involves an area and a radius? Area equals pi r squared. That is the hard part. You just did the hard part. Trying to give you confidence until I just smash it into pieces momentarily. That's the hard part. I mean, I think these things are easy, but everyone I tutor, like, these are so hard. And just like, well, yeah, because there's 1,000 different types of questions out there. Like, we're not going to do every type of ever-existing related rates questions because there's just so many of them. And then some jerk invents, like, a really hard one later on. I'm like, okay. So I need to find dA dt. I need to differentiate this. So what's the derivative of A? And this is the exercises we just did. dA over dt equals 2 pi r dr over dt. And then you plug it in. So what happens when you plug everything in? We don't know dA over dt, so that stays. Equals 2 pi, what's r? 4 times 1. And what do you get? And a lot of the times, this is usually not calculator. So it's 8 pi what? It's area. So area is changing over time. So this is going to be feet squared per, what time do we have? Seconds. It's kind of rare that there'll be jerks about the time. Like sometimes they'll say like this is like 1 inch per second, and they want to know like, and they'll give you like the radius of feet, and they'll give you, that's a units conflict. You just need to make sure all the units match up. Or sometimes they'll give you like per second, but they're asking per hour. It's very rare they're jerks like that, but just kind of pay attention just in case. How was our first related rates problem?
Straightforward.
All right.
Why do we tag?
It's chain rule.
So like,
Every single time.
like why? What is tagging though? Like that's what something is.
Because every single time you take a derivative, you're changing something. Every single time. So anytime you have a variable. So that's essentially what the tagging is. Is whenever a variable change, you just have to state it. Because this is really like change of A. Like in physics, they'll say, what's the change of A? I'm sure you might have seen that. Delta A. And then equals 2 pi r changing r. Because r is changing as you take the derivative. And A is changing as they take the derivative. So this is just a mathematical way to write that out.
And then what about like how we've usually done it? How come we don't do like dx or dy over dx?
We have when we did implicit.
Implicit, yeah, but how not regular?
Because then you would get, like, if you take y equals x squared, you're going to get dy over dx, which we have done, equals 2x dx over dx. What's dx over dx? It's just 1. So that's why we have never written it. So scribble that out in case the YouTube viewer is very confused. Number 2, we have air being pumped into a spherical balloon. I wonder what shape we're going to be figuring out. At a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So this is one of those where it's going to be a little bit of finagling here. This one isn't as straightforward, so let's go for it. So what do we know? Okay, so it's cubic feet per minute, so that's going to be dV dt. Because it's volume. Cubic feet is volume. Cubic anything is volume per minute. So that's why it's changing volume over changing time, which is 4.5. Anything else that we're given here? R equals 2. Anything else we're given, or what are we looking for? So how do we write that out? So if this is free response, by the way, this gives you 1 point. You can be clueless and write down everything correctly and get a point. Okay, so what formula do we know that has to do with the sphere and volume? It's make sure it's r cubed. You do need to know these things. You do need to know your geometry. This is what I was saying. Geometry is the hard part. You need to know geometry. Am I ready just to start taking derivatives? Yep. Let's do it. What's the derivative of the left? What's the derivative of the right? I hear you mumbling it, so I'll just write it down with you. Alright, let's plug in what we know. What can we plug in? Okay. That's kind of whacked out, so I have to do a little bit of solving here. So we're going to get 4/3. Hey, can I just say that this 3 on the bottom and that 3 just cancel out? Sure. We're cool with that? No? No! Oh my god. Losers. 4 pi times 2 squared GRDT. Because r is equal to 2. I'm plugging that 2 in. And that's a 4/3 on bottom and a 3 right there. I just, casually just, say see you later. That happens every single time I take the derivative of this formula. Every single time. Look at this. This is what we did for the warm-up. Doesn't that 3 and that 3 always cancel out? Every single time. Let's solve for GRDT. So, let's do Algebra 1 math at this point. What's 2 squared? 4. Times 4? So 4.5 equals 16 pi. GRDT. And then what do I do to get GRDT by itself? So it's going to give us DRDT equals, and that's good enough. What's my unit? That's and that matters. It's radius, so how many dimensions does it have? It's one-dimensional. Are you sure it's squared? One-dimensional. I'm aware of this. And usually, these are 3-point questions on a free response. So your givens is 1. Your work right here is usually 1. And your units is usually 1. You could steal 2 out of 3 points here by doing a lot of things wrong. Okay? These problems, you want them to be free response because you can easily get points for making mistakes. Easily. Now, I'm sure you're asking yourself, how could this get so difficult? I mean, I'm just going off I haven't looked at the bottom question yet. You really think I look ahead? What if I asked you for DADT? You would have to do everything we just did. Because if we needed to find dA over dt, because we know A equals pi r squared, and dA over dt is equal to 2 pi r dr over dt, I can't do this problem because I don't have dA over dt and I don't have dr over dt. So you would need to do this problem to figure out what dr over dt is, and then you would plug it in and solve for dA dt. But if this is like a part B question, you already did all the hard work. Now you're at easy part. I'm just giving you a heads up on how this stuff gets a little bit more challenging. Let's do number 3. Watch, this is exactly the same thing. So it looks like we have a cylinder here. So let V be the volume of the cylinder having a height h, radius r, and assume that the h and r vary with time. At the certain instant, the height is 6 and increasing at 1 inches per second, while the radius is 10 inches, decreasing at 1 inch per second. How fast is the volume changing at that instant? Is it increasing or decreasing? This is a very, very straightforward one. Do you want to give us a try on your own?
Yes.
Very straightforward.
Yeah.
Okay. I'm going to give you a hint. You need to do product rule. But other than that, it's very straightforward. So give 3 a try. I'll straggle behind a little bit. If you didn't know the formula, it's pi r squared h. Again, geometry. Just on my print out your worksheet. Say anything stupid, I'll know. I'll report it. Check your product rule. That's 6. What's DHTT? It's 1. Negative 20 pi. What's our units?
Hold on.
Inches cubed per second. Is this increasing or decreasing? Why? Because it's negative. People will get problems like this wrong because they'll write the volume is decreasing at negative 20 pi. I'm going, well, you just called it increasing. If you're decreasing at a negative rate, you're increasing. You can say it's increasing at negative 20 pi, or you can just say decreasing at 20 pi. Don't say decreasing at negative, please. People get that stuff wrong. Alright, so what? We did 3 problems in about 30 minutes. Problems take a little while. We have like 5 more problems to do. And the main reason I'm going to do all 5 of these we have 5 more problems to do. I'm going to go through them a little faster. The main reason is because there's so many different types of problems. I kind of want to expose you to like just about all of them. Some of them go like really quick, some of them not so much. Like here, in number 4, we have this stupid stone in a water problem. I think it's the same problem. Same problem. Boom. Move on. Hey, here's the ladder problem we're talking about. What's the answer going to be, Mason? 2. Okay, we'll see. Not even close, but we'll see. Okay, so we have a 17-foot ladder leaning against the wall. The bottom of the ladder is pulled along the ground away from the wall at a constant rate of 5 feet per second. How fast will the top of the ladder be moving down the wall when it is 8 feet above the ground? Yes. Do you think that would be helpful?
I think yeah.
Okay. Pictures. I'm not. Okay, fine. I'll do this. There. Okay, what do I know? What's it? Okay, what variable do I call that? C. Let's call that C. So I'm going to call this A. I'm going to call this B. I'm going to call this C. Okay. Reason is because we're probably end up using the Pythagorean theorem here. So what do I know? So the bottom of the ladder is being pulled away. Okay. So what does that mean? The bottom is getting pulled away. So what's changing? So dA over dt is equal to 5 feet per second. What else do I know? What's B? Anything else? I have C up here. I mean, you can put it down wherever you want. Doesn't matter. All right, what am I looking for then? How fast will the top of the ladder be moving down? So this is a rate. No. dB. Because I'm looking for how it's, CB is the height right here. So how fast is it moving down the wall? So that's a rate. Okay, so how can we relate this problem? Pythagorean theorem, so we got a squared plus b squared equals c squared. So what do we do now? Yes. Are you scared of me or something?
No, I was just gonna wait till the end of class.
To get the notes?
Yeah, then just watch the video.
No one's scared of me. Just my wife. Don't tell her I said that. I'm really scared of her. I hope she doesn't watch my videos. Honey, I'm so sorry. Forgive me. She doesn't have time to watch my videos. Okay, so let's take the derivative. So what's the derivative of a squared? Plus. yeah, that. Equals? Okay. Do we have everything here?
Probably. We have DC or DC. Most things.
Let's talk about that. What's DC over DT? This is the rate at which the ladder is changing. The ladder is falling. Is the ladder changing size? The ladder is not changing size. This is 0. How much easier does that make this problem?
Maybe. Does it actually?
Yes.
We wasn't saying anything. So it's just all equal to 0 then?
So then to the right-hand side is 0 because ladder's a constant. Ladder's not changing. The ladder's just falling down, but the hypotenuse is not changing length. It will always be 17 feet long. At least in the moment of this problem, it's always 17 feet long. I mean, it hits the ground and like an inch chips off at the end. Okay, there's actually one more variable we don't have. We don't have A. How come in the world can we solve for A? Yeah, so don't we have this triangle? 17, and then this is 8, and this is A. If you know your Pythagorean triples, it goes a lot faster. What's A? I like this guessing.
There's only so many numbers that it could be. So like
15. Yeah, me too. Get 150 plus 16 dBdt equals 0. 16 dBdt is equal to negative 150. So what's dBdt? Negative 150 over 16. If it's if it's a free response, you don't need to simplify. So we're good here. What's my rate? What's my units for my rate? I have it up here. No, we're not doing area. No squared. No, we're not doing acceleration. Yeah. Now, some people will answer this saying it's falling down at a rate of negative 150 over 16 feet per second. Why do they lose the point? Yeah. First off, you did writing. Where's Jono when I need him? Because he'll be the one to do that. And I want to pre-yell at him. So, if you say it's falling down at a negative rate, that really means it's actually going up. So just be careful on that. Bless you. Okay, I'm trying to figure out which problem I want to do here between 6 and 7. We can either do another ladder problem that involves an angle, or we can do a rocket problem that involves an angle. No.
yes. That is what works.
I'm having so much fun. I don't want a break. Want a what? A rocket? Let's go outside and do the problem. No, let's not waste our time. All right, so a spy tracks a rocket through a telescope to determine its velocity. The rocket's traveling vertically from a launching pad located 10 kilometers away from the spy. Certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3 and is changing at a rate of 1/2 radians per minute. What is the rocket's velocity at that moment? Because I'm sure when they wrote this 1/2 in the Microsoft Word, it didn't work out well. All right, how do I know it's a triangle first off? Because it'd be rude if it wasn't. If it's going to talk about radians and theta, it's going to be a triangle. Okay, so what do we know here? How can we label this triangle? Okay. Okay, and then this is the rocket. I'm going to call it R because it's a rocket. Now, the reason I'm labeling this 10, is that 10 ever going to change? Okay, no, not from this experiment. The rocket, that's going to change. That's changing. Okay? And I'm also going to be using this theta right here. So let's go through and start labeling off our givens here. So I already have the 10 labeled. What else do we know? He's behind the bushes. Okay. All right. Let's get through the problem. All right, we're having so much fun with the spy behind the bushes. Look at this rocket that's going up. What else do we know? What's theta? Theta's changing, right? Because as this rocket goes up, theta is going to be opening up more and more and more and more and more. Okay, so what is d theta dt? Gives us this. What else do I know? That's it? Oh gosh darn it all. Yeah, I think that's good though. What are we looking for? Okay, so what is that going to represent? dr dt. dr dt equals? We don't know. Alright, how can we relate these together? We need to relate an angle and an r that are the opposite side of our triangle and the adjacent side of the triangle. Tangent theta equals r over 10. Again, this is geometry trig. This is still geometry trig. This whole setup is all geometry trig. You could have done this in geometry. Like, not like the changing part, but like, you could have figured this out. The d theta, or tangent theta equals r over t. Like in geometry, they would ask you, solve for r. I'm making fun of you. Is that how it comes off? Very condescending?
No. I didn't hear what happened. I mean a little bit.
Whatever. Okay, so now I have the formula. What do I do now? Derivative. What's the derivative of tangent of theta? Secant squared theta d theta dt equals, what's the derivative of this side? Yeah, 1/10 dr dt. You remember that, like, stuff you need to know from calculus that I gave you? That's Jason's memorial. We'll call that, not you, the other one. That's when I have him staple everything. We'll just call it Jason's memorial packet. Yeah, that's got this information on here in terms of... Every time I see him, I swear, he always does this. It makes me so happy. Okay, let's plug in what we know. What do we know? No! Well, you need to, like, not be a loser anymore then. Alright, secant of pi over 3 squared, do that in a second. What's d theta dt? And then 1/10, I don't know, dr dt. You do need to know secant of pi over 3. If you don't know, what's the reciprocal of secant? What's the reciprocal function? It's cosine. What's cosine of pi over 3? It's 1/2. Now, what's the reciprocal of that? 2. So secant of pi over 3 is... No, it will be 2 in a second here, and then it'll not be 2. Okay, so it's 2 squared times a half. What's the RDT? So, sorry, I want to write this in dRdt. So dr over dt is equal to 20. What? I'm not going to. I just can't wait. Please don't say squared.
I want to say squared.
It's r, so it's not radians. It's a height, so it's gonna be kilometers. No. Okay, 7, just another angle problem. You can try that one on your own if you want to at another time. Check the notes. Yeah, well, all we're doing for that problem is we're just seeing like what the angle changes. All right, so last year I taught BC. I gave a problem like this on a test, and everyone got it wrong except for one kid. Dead serious. And when I show it to you, you're gonna be like, "How the heck did they get it wrong?" Very similar to this question. And I absolutely belittled all of them. Because it was BC, I was even more condescending to them. Okay, so we got a man who's 6 feet tall, walks at a rate of 5 feet per second away from the light. That is 15 feet above the ground. At what rate is the tip of the shadow moving when he is 15 feet from the base? So pretty much is what I got here. And then here's like the light. I don't know how to draw a light. I can draw like a sun. Street light. Hey, don't be criticizing my thing that looks like animals. If I were to draw a spider, you'd be like, that's a light. Oh my god, alright. What do we know? Okay, man 6 feet tall. Alright, M for man?
Sure.
So M equals 6. What else do we know? We know the light's also 15, right? So light's 15. We agree that right here, this is the shadow. Because it's being blocked, this is the shadow. And then this is the distance between the man and the light. So what else do we know here? So do I have the 5 feet? What's the rate mean? Which one's the rate? He's walking away from the light. He's walking this way. So what's changing? The D. So we have d dt is equal to, let's give it 5. Because the distance is increasing. It's not decreasing. Anything else we need here? When he's 10 feet from the base, so that's D equals 10. And then we need to find the shadow, which is going to be? Okay, so let's go back to geometry. How can you make a relation out of a triangle here inside of another triangle? You're just making a proportion. Let's do a proportion of the big triangle. What is the height of the big triangle? all over what is the length of the big triangle? S plus D. Shadow plus the distance. Equals, what's the little one? Over. I would not take the derivative yet, because this looks like it would be scary if you did. Let's go ahead and solve for it. We'll figure out how unscary this is. So how would you solve for this back in geometry? Cross multiply. So you're going to get 15 S's equals 6S plus 6D. Not 6D, but 6D. I could probably do one more thing of math here. What can I do? Subtract 6, so I have 9S equals 6D. Now is this nice and easy to take a derivative? So let's take the derivative of the left. What do you get? Equals 9 times ds dt equals 6 times 5. From here, it's just algebra. Could simplify if you want. I'm not going to out of sheer laziness to show you don't really need to. If it's multiple choice, then I'm sure, hopefully you can figure out what that would be. Mason, let's end on a high note. Give me my units. I'm not going to.